All right, next up is question 7. This says, consider the vector field f, which is minus 4y minus 5x, and the region D, which is bounded by the parabola y equals 36 minus x squared and y equals 0. All right, so here is our region D, here is our vector field. Part A asks us to compute the two-dimensional curl and divergence of this field, so pretty straightforward there. Your I component P is minus 4y and your J component Q is minus 5x. So the curl comes out to be -1 and the divergence is 0. So in other words, the vector field here is source free throughout all of R2. All right, part B says compute both of the integrals in the circulation form of Green's theorem to illustrate their equality. Okay, so here is the circulation form of Green's theorem. So we'll go ahead and start by computing this line integral on the left, which does take some work because you'll notice here for the boundary of our region D, we have to break this up into two pieces, right? We have the straight line segment where y is 0, and then we have this parabolic portion of the boundary. Okay, so when y is 0, I'll just parameterize that as r1 of t is t comma 0, where t varies from -6 to 6. So that's giving us a left to right parameterization. And then for this parabolic portion, where y is 36 minus x squared, I'll just set x to t, and y then would have to be 36 minus t squared. And I'll let t vary from -6 to 6, but now we got to be really careful here, okay? To get a counterclockwise orientation of this boundary, right, I need to be moving from right to left as my parameter t increases. But notice from this parameterization I gave, this would actually start us over here when t is -6 at the point -6, 0. And then as t increases, I'd actually be moving from left to right. So there's a few ways around this. I think the easiest way is just to keep this parameterization as it is. But then when we get the corresponding integral over the parabola, just put a negative in front of it. Okay, another option is to just change this orientation. So for example, I could replace t with -t, and then I'd have to adjust this as well. That would be a perfectly fine way to do it, and then you wouldn't have to introduce that negative. But I'm going to go ahead and stick with this option. Okay, so now let's go ahead and compute the line integrals over these two portions. So the first thing I'm doing here is I'm just rewriting uh, each integral over piece 1 and piece 2 in terms of our vector field f evaluated along each respective path and then dotted with the corresponding tangent vector, so r1 prime and r2 prime. And notice I put that minus in front of the integral over path 2 there, just to reflect that reverse in orientation. Okay, so now what is our vector field f evaluated along R1? Well, I'm going to set x to t and y to 0. So if y is 0, my I component would be 0. That's what I got here. And then if I set x to t, I'm going to get minus 5t for my j component. And that's what I get here. Now R1 prime, that's just 1 comma 0. So I get this right here, which is pretty simple. All right. And then for f of r sub 2, now we're going to set x to t and y to 36 minus t squared. So that's going to give us minus 4 times y, which is 36 minus t squared, comma, minus 5t, since x is t for the j component there. And then r2 prime, that would just be 1 comma minus 2t. Okay, so the benefit here is that this dot product is 0, and this dot product is a little bit messy, but it's not too bad, so go ahead and bring that up. So you get 0 there. This turns out to be 14t squared minus 144. So it all boils down to integrating this quantity 14t squared minus 144 from -6 to 6 with that negative out in front again from the orientation reversal. It all boils down to a value of minus 288. Okay, so, fair amount of work there. Let's now tackle the double integral. All right, so I'll make a little space here. Okay, Double integral is a heck of a lot easier. Okay, we're just going to integrate the curl over this region D here, and the curl is constant -1. So if I'm integrating a constant over D, that's just going to be that constant times the area of the region D. So in other words, it's just going to be the opposite of the area of this region D. And I can compute that just using a single variable integral. I'm just going to integrate from -6 to 6 the function 36 minus x squared. And that turns out to be -288. So these two integrals are the same. All right, cool. So now let's go ahead and move on to part C. This is asking us, sorry, I need to make a little space there. All right. Yeah, no, we're good. So let's go ahead and look at the flux form of Green's theorem. So we have that the flux integral here is equal to the double integral of the divergence of our vector field. Okay, and since the field is source free, we know the answer is going to be 0. This is really, this was just part B of question 6 in the last video. But nonetheless, I will still illustrate the computation here for the line integral. So let's go ahead and go through that. So we have that same parameterization as we did for part B. And so I'm going to evaluate my vector field along R1, but now I have to dot it with R1 perpendicular prime, right? So that's where, here, I'll bring that up. Okay, so that's where I take R1 prime, which is just 1, 0, and then to get the outward unit normal, okay, because this is the unit tangent vector, so the outward unit normal, that's where I just swap the coordinates and I stick a negative in front of what the I component is for R1 prime. So I get the vector 0, -1. It's just the vector -j, right? It's pointing directly outward of our region here along the x-axis. Okay, so that's going to go in here. Now the evaluation of your vector field along R1 as well as R2, those parts are the same as the previous calculation. Now for R2 perpendicular prime here, here R2 prime is just 1, -2. So we swap coordinates and then we stick a negative in front of the I component for R2 prime. So we get this. And so then if you crank out these dot products, a little messier, we get 5t from this, and then a -8t cubed plus 293t from this part. And keeping in mind that there is this minus in front of this integral, when you combine those, you wind up getting this. And I could, of course, combine the t's, but I'm just writing it this way just to emphasize you're getting this contribution and this contribution. Now, here's the deal. This integrand is odd, and I'm integrating over symmetric limits with respect to t. So the integral is 0. Okay, so at least it sort of finishes nicely, but it is definitely a bit of a mess. Now, the double integral, on the other hand, couldn't be easier, right? Because the divergence being 0 just immediately implies that the double integral is equal to 0. So again, these two integrals are the same, and that's going to do it for this question. All right, thanks so much.